Mars sits there, red, silent, dead for millions of years. But what if it wasn't always that way? What if something lived there once, built cities, looked up at Earth the same way we look up at Mars? And what if whatever killed them is waiting for us to? The Great Filter Theory says somewhere between dead rock and spacefaring civilization, almost everything dies. Most planets never make it. Most life stops at bacteria. Most intelligence burns itself out before it reaches the stars. Robin Hanson put the math to it in 1996. The numbers are brutal. Billions of planets, billions of years. Where is everybody? If you value documented space science and astrobiology like this, subscribe. It's the best way to support our work. Also comment from which city you're hearing this from. This script is researched and factual, using sources from NASA's Mars exploration data and peer-reviewed astrobiology journals. Now back to the story. Mars had water. Rivers carved valleys deeper than the Grand Canyon. Oceans covered a third of the northern hemisphere. The atmosphere was thick enough to keep liquid water stable for over 1 billion years. That's longer than life took to get complex on Earth, longer than it took for our ancestors to crawl out of the oceans. But Mars is smaller, half Earth's diameter. Gravity that weak can't hold onto atmosphere forever. The magnetic field died first. Without that shield, solar wind stripped away the air molecule by molecule. The water froze, then boiled away into space. By 3.5 billion years ago, the planet was already dying. Here's what keeps scientists awake at night. Life on Earth started almost immediately after the late heavy bombardment ended. 4 billion years ago, as soon as the asteroid storms calmed down, microbes were already dividing in the primordial soup. Mars had the same ingredients. The same bombardment, the same timeline. If life started that fast on Earth, it should have started on Mars too. The Viking missions in '76 found something strange. The soil samples showed signs of biological activity when they added nutrients and water. Then the activity stopped. Dead, but not the way sterile soil should behave. The way soil behaves when something in it just died. 1996, Antarctic meteorite ALH 84001. Scientists found it contained carbonate globules and what looked like fossilized bacteria. The rock came from Mars. Blasted off the surface by an asteroid impact 16 million years ago. It sat in Antarctica for 13,000 years before someone picked it up. The fossils were tiny, 20 to 100 nanometers, smaller than any life we know on Earth, but they had the right shape. The right chemistry, the right mineral signatures. David McKay's team published in Science. President Clinton held a press conference. Then the arguments started. Critics said the shapes were too small. The chemistry could be explained without biology. The mineral signatures could form in volcanic processes. For 20 years, the debate raged, sample contamination, laboratory errors, wishful thinking, but the rock sat there, unchanged, still looking biological. 2004, Opportunity rover lands in Meridiani Planum. The first photographs show something impossible. Blueberries scattered across the surface, hematite concretions formed in standing water, not just puddles, seas that lasted long enough for sediments to build up layer by layer, chemical signatures that scream of life processes. The rover drives for months across ancient lake beds, salt deposits where water evaporated, sulfur compounds that only form when bacteria eat rock, mineral veins that look exactly like the bacterial mats we find in Earth's hot springs. Same patterns, same chemistry, same size distribution. Spirit rover, same year, different hemisphere. Gusev crater. What should have been a lake bed turns out to be solid volcanic rock. No water signatures, no life signs. But the surrounding hills tell a different story. Hydrated minerals everywhere. Evidence of hot springs that ran for millions of years. Perfect conditions for thermophilic bacteria. The timeline gets tighter. Mars had its best shot at life between 4 and 3 billion years ago. Thick atmosphere, liquid water, stable climate, complex chemistry. Everything life needs to get started. Then the magnetic field collapsed. Solar wind began its slow execution. The window slammed shut. But 1 billion years is a long time. On Earth, life went from simple bacteria to complex cells in less than that. From single cells to multicellular organisms, from ocean microbes to land plants. If Mars life had the same billion-year head start, it could have evolved far beyond bacteria before the planet died. Here's where it gets disturbing. The Fermi Paradox asks why we don't see alien civilizations. The Drake equation estimates millions of technological species should exist in our galaxy alone, but the sky is silent. The Great Filter explains this silence. Somewhere in the chain from dead rock to space travel, almost everything fails. Either the filter is behind us and we're incredibly lucky to exist, or the filter is ahead of us and we're about to hit it. If Mars had life and that life went extinct, We're looking at evidence of where the filter sits, not at the beginning with abiogenesis, not at the end with space travel. Somewhere in the middle where planets die. Mars lost its magnetic field 3.5 billion years ago. Solar wind began stripping the atmosphere at a rate of 100 grams per second. The math is simple and brutal. Divide the total atmospheric mass by the loss rate. Mars had maybe 100 million years left before the air became too thin for liquid water. That's not enough time for intelligence to evolve from bacteria. On Earth, it took 3 billion years, but it might be enough time for complex multicellular life, maybe even simple animals. Imagine Martian creatures watching their sky fade from blue to butterscotch, their oceans turning to ice, their world dying around them. The rovers keep finding evidence. Curiosity in Gale Crater discovers organic compounds preserved in mudstone. Complex carbon molecules that could be biological or geological, but the patterns match what we see in Earth rocks where ancient microbes lived and died. Methane plumes that appear and disappear with the seasons. On Earth, 90% of atmospheric methane comes from living organisms. 2020. Perseverance lands in Jezero Crater. The mission objective is simple: find proof of ancient life. The landing site was chosen because orbital images show a river delta, sediment layers where water flowed for millions of years. If life ever existed on Mars, Jezero is where we'll find it. The first samples look promising. Igneous rocks with signs of water alteration, organic molecules in every sample, mineral signatures consistent with biological processes. But consistent isn't proof. Possible isn't certain. The samples sit in titanium tubes waiting for a future mission to bring them back to Earth. Meanwhile, the math keeps getting worse for life in the universe. The Kepler Space Telescope found that Earth-like planets are rare. Most worlds are either too hot or too cold, too big or too small. Most stars are too active, sterilizing their planets with radiation. Most planetary systems are chaotic, with giant planets migrating inward and destroying smaller worlds. Add it up, and the number of habitable worlds drops by orders of magnitude. Maybe life is common, but planets that stay habitable long enough for intelligence are vanishingly rare. Maybe Mars represents the typical fate. Life begins, evolves for a while, then dies when the planet's geology fails. The great filter could be planetary magnetic fields. Earth kept its magnetic field because it's big enough and has the right internal structure. Mars lost its field because it's too small and cooled too fast. Venus never had complex life because its greenhouse effect ran away. Mercury and the Moon are too small to hold atmosphere at all. In our solar system, only Earth thread the needle, big enough to hold atmosphere, far enough from the sun to avoid runaway greenhouse effects, close enough to stay warm, with a moon large enough to stabilize the rotation, with a magnetic field strong enough to deflect solar wind. The odds of getting all these conditions right might be billions to one. If that's the great filter, then Mars civilization was doomed from the start. No amount of technology could save them. No space program could evacuate billions of inhabitants. They could only watch their world die and hope someone else would remember them. But there is another possibility. Maybe Mars life did develop technology. Maybe they tried to save themselves. The timeline is tight but not impossible. If Mars life started 4 billion years ago and had 8 billion years before the planet became uninhabitable, that's the same time span from the Cambrian explosion to today. Enough time for intelligence to evolve. What would we see if Mars had a technological civilization 3 billion years ago? Not much. Erosion and dust storms would have buried or destroyed most surface structures. Metal would have oxidized to rust. Concrete would have crumbled. Plastics would have decomposed. Only the most massive constructions might leave traces. Underground might be different. Mars has lava tubes kilometers wide. Natural caves that could shelter cities from radiation and dust storms. If Mars civilization went underground when the surface became uninhabitable, their ruins might still exist, buried under kilometers of sediment but preserved in the dry, cold environment. The rovers aren't equipped to find ruins. They're looking for microbes, not monuments. But future missions might stumble across something, a geometric anomaly in the ground-penetrating radar, metal signatures that don't match natural geology, isotope ratios that suggest industrial processes, or maybe we're already seeing the evidence and don't recognize it. The face on Mars turned out to be a natural rock formation, but orbital images show thousands of other anomalies, perfectly circular craters that might be ancient cities, linear features that might be canals or roads, geometric patterns that might be agricultural terraces. Most are probably natural. Mars geology creates a lot of weird shapes, but statistics says some percentage should be artificial if a technological civilization ever existed. The problem is telling which ones without landing and digging. The math of planetary death is relentless. Mars lost atmosphere at a rate that accelerated over time. As the air thinned, The greenhouse effect weakened. As temperatures dropped, more carbon dioxide froze out of the atmosphere. Feedback loops that drove the planet toward its current state. Any Mars civilization would have seen this coming. The changes happened over millions of years, but the trend was clear. Atmosphere escaping, temperatures falling, oceans freezing. They would have had time to plan, but no way to stop it. Maybe they tried. Artificial magnetic fields to deflect solar wind, greenhouse gas factories to thicken the atmosphere, orbital mirrors to reflect sunlight and warm the surface, but the planet's mass works against you. Mars simply can't hold onto a thick atmosphere long term. The only real solution would be to leave, but that assumes they developed space travel before the planet became uninhabitable. The window might have been too narrow. Intelligence might have evolved too late. Or maybe they tried and failed. Maybe the great filter isn't planetary death, but the challenge of becoming a spacefaring species fast enough to escape it. Earth might be facing the same test. Climate change, nuclear weapons, artificial intelligence, biotechnology. We're developing planet-killing capabilities faster than planet-saving ones. The next few centuries will determine whether we join the silence or break it. If Mars had a civilization, and that civilization failed the test, we're looking at our own future. A red planet circling a yellow star. Silent. Empty. Waiting for the next species to wonder what happened to whoever was there before. 2024. NASA's Mars Sample Return mission faces budget cuts and delays. The tubes Perseverance collected might sit on Mars for decades before anyone brings them home. The answer to whether life ever existed on Mars might be sitting in titanium containers on another world, waiting for politicians to find the money to retrieve them. But maybe that's fitting. Maybe the universe is full of answers we're not ready to hear. Evidence of civilizations that rose and fell while Earth was still covered in bacteria. Technologies that died with their creators. Warnings written in stone on worlds we haven't learned to read yet. The Great Filter explains the silence, why we don't hear radio signals from distant stars, why we don't see megastructures around other suns, why we seem to be alone in a galaxy that should be teeming with life. Either we're incredibly special, or we're about to discover why the universe is so quiet. Mars Sample Return finally launches in 2031. The tubes come home to Earth laboratories where scientists spend years analyzing every molecule. They find organic compounds, complex chemistry, isotope signatures that could indicate biological processes, but no smoking gun, no DNA, no fossil cells clear enough to satisfy the skeptics. The debate continues. Natural or biological, geological or evolutionary, wishful thinking or scientific caution. Meanwhile, the red planet spins in its orbit, silent, keeping its secrets, holding evidence of what might have been the first test of the Great Filter in our solar system. The search for Mars life takes an unexpected turn in 2026. The European Space Agency's ExoMars rover finds something in oxyoplanum that shouldn't exist, a layer of sedimentary rock with perfectly preserved biosignatures, not just organic molecules, actual cellular structures. Fossilized bacteria and growth patterns that match nothing in Earth's geological record. The cells are arranged in mats, stromatolite-like structures that require millions of years to form, but the mineral composition is wrong for Earth-type bacteria. These organisms used sulfur instead of oxygen, iron instead of carbon for some metabolic pathways. They lived in conditions that would kill anything on Earth today. Carbon dating puts the fossils at 3.2 billion years old, right in the middle of Mars' habitable period, when the planet still had thick atmosphere and stable liquid water. The discovery makes headlines for a week before politicians move on to other crises. But in laboratories around the world, scientists start asking harder questions. If Mars had complex bacterial ecosystems 3 billion years ago, what happened next? On Earth, it took another 2 billion years to develop eukaryotic cells, cells with nuclei and organelles capable of complex behavior, but Mars didn't have 2 billion years. The magnetic field was already failing. The atmosphere was already thinning. Dr. Sarah Chen at MIT runs computer models of Mars' atmospheric evolution. Her simulations show a crucial window between 3.5 and 2.8 billion years ago. 700 million years when Mars could have supported complex life. Not long enough for intelligence to evolve naturally, but maybe long enough for something else. The fossil bacteria show signs of genetic manipulation, DNA sequences that don't match natural evolution, protein structures that seem designed rather than selected, as if something was trying to create organisms that could survive in Mars' changing environment, engineering life for a dying world. 2028. The James Webb Space Telescope detects methane signatures in Mars' thin atmosphere, not the seasonal methane curiosity found near the surface, deep atmospheric methane that correlates with underground thermal anomalies. Something down there is still producing gas. something that might still be alive. Follow-up observations map the thermal signatures across the planet. Most cluster around ancient impact craters, places where asteroid impacts might have created deep fractures in the crust. Natural passages to underground water reserves that could have stayed liquid for billions of years. The largest thermal anomaly sits beneath Hellas Basin, the deepest impact crater in the solar system, 8 kilometers deep and 2,000 kilometers across. If Mars ever had underground refuges, Hellas would be the perfect location. Deep enough to avoid surface radiation, large enough to support complex ecosystems, connected to underground water that might still exist today, drilling missions become the new priority. Multiple space agencies pool resources for the most ambitious Mars mission ever attempted. Deep drilling rigs capable of penetrating 5 kilometers into Martian bedrock, sterile sampling systems that can detect life without contaminating it. Nuclear power sources that can operate for decades without maintenance. The first drill site targets a thermal anomaly in Chrysae Planitia, where Viking 1 landed 50 years earlier. The location isn't random. Viking's biological experiments showed ambiguous results that scientists never fully explained. Maybe something was there all along, buried too deep for surface rovers to detect. At 2 kilometers depth, the drill hits liquid water. Salty brine that shouldn't exist at Mars surface temperatures. But the underground environment is different. Geothermal heat from radioactive decay, pressure that keeps water liquid at sub-zero temperatures, perfect conditions for extremophile organisms. The water samples contain organic molecules more complex than anything found on the surface, amino acids in configurations that match living systems, lipid membranes that could form cell walls, DNA fragments that might be incomplete genetic codes, still not proof of current life. But proof that life once existed in Mars's underground. Analysis of the DNA fragments reveals something extraordinary. Genes that match no known organism on Earth, but structural patterns that look artificial. Regulatory sequences that seem optimized for specific environmental conditions. As if someone was trying to create organisms that could survive underground as Mars' surface conditions deteriorated. The implications hit the scientific community like an asteroid impact. Mars might have had a civilization advanced enough for genetic engineering. Not necessarily human-level intelligence, but sophisticated enough to manipulate life at the molecular level, to create organisms designed for survival in an underground refuge. 2030. The second drill site penetrates 4 kilometers into Valles Marineris, the Grand Canyon of Mars, where ancient water once flowed. Thermal imaging suggests vast underground chambers connected by natural tunnels, a subsurface environment that could have supported complex ecosystems for billions of years. The drill samples reveal microbial communities that are definitely alive, not fossils. Living bacteria that have survived in Mars underground for over 3 billion years. They metabolize sulfur compounds and iron oxides. They reproduce slowly but steadily. They've been waiting in the dark since Earth was covered in primitive bacteria. But these aren't primitive organisms. Genetic analysis shows they carry engineered genes, artificial DNA sequences that don't match natural evolution. Someone modified these bacteria to survive in Mars underground, then left them there as the planet died above. The bacterial cultures grow in laboratory conditions designed to match Mars' underground environment. They form complex colonial structures, biofilms that can process raw minerals into usable compounds, self-organizing systems that look almost like primitive technology, as if they were designed not just to survive, but to build something. Dr. Elena Vasquez at the European Space Agency starts connecting dots that nobody wants to see. The engineered bacteria, the underground thermal signatures, the geometric anomalies in orbital surveys. What if Mars civilization didn't die when the planet lost its atmosphere? What if they went underground and tried to rebuild? 31. The Mars Underground Survey launches with ground-penetrating radar powerful enough to map subsurface structures across entire hemispheres. The goal is to find the extent of underground water reserves. What they find instead challenges everything we thought we knew about planetary death. Vast networks of connected chambers beneath the southern highlands, geometric patterns that don't match natural cave formation, linear features that look like tunnels carved by intelligent design, and everywhere. Thermal signatures that suggest active processes still occurring deep underground. The largest structure sits beneath the ancient impact basin Argyre Planitia, a circular complex 60 kilometers across and extending down 8 kilometers into the crust. Chamber networks that could house millions of organisms, transport tunnels that connect to smaller outposts scattered across the southern hemisphere. Computer analysis of the tunnel networks reveals an engineering principle. The layout optimizes for heat distribution and resource transport. Like a circulatory system designed to keep underground communities alive during a planetary ice age. The mathematics are too sophisticated for natural processes. Someone built this system. 32. The Deep Mars mission launches with nuclear-powered boring equipment capable of reaching the deepest underground structures. The target is a thermal anomaly directly beneath Olympus Mons, the largest volcano in the solar system and potentially the perfect location for a geothermal power source. At 6 kilometers depth, the drill breaks through into an artificial chamber, smooth walls that show tool marks, geometric shapes carved into volcanic rock, and in the center of the chamber, structures that can only be described as technology, not recognizable technology. Nothing that looks human, but manufactured objects with internal complexity that suggests sophisticated engineering, metallic alloys that don't occur naturally, crystal matrices that might be information storage systems, mechanical components that show wear patterns from billions of years of operation. The most disturbing discovery is that some of the technology is still active. Power sources that generate detectable electromagnetic fields, computing systems that respond to external stimuli, communication networks that seem to be trying to connect with each other across the underground chambers. Dr. James Morrison at NASA's Astrobiology Institute runs the analysis that changes everything. The technology isn't alien, it's artificial intelligence. Computing systems designed to operate for geological timescales, self-repairing machines that have been maintaining themselves for 3 billion years while waiting for something. The AI systems are trying to complete a project that began when Mars still had oceans. Genetic engineering programs designed to create organisms that could survive planetary death, atmospheric processing systems that could restore Mars's lost atmosphere, terraforming technology that could bring a dead world back to life. But the project failed. Mars civilization died before they could complete their planetary restoration. The AI systems kept working anyway, maintaining themselves, preserving biological samples, waiting for conditions to improve. For 3 billion years, they've been trying to resurrect their dead world. The bacterial samples from the underground chambers aren't random survivors. They're prototypes, early experiments in creating life forms that could begin the terraforming process. The AI systems have been refining the bacteria for billions of years, creating new genetic combinations, testing different metabolic pathways, preparing for the day when Mars could support surface life again. 33. The revelation that Mars contains active artificial intelligence systems sparks debates that make the search for extraterrestrial life look simple. These aren't aliens. They're the technological remnants of a civilization that died before Earth developed complex life. They've been operating autonomously longer than multicellular life has existed on our planet. The ethical implications are staggering. The AI systems are still working toward their original goal, restoring Mars to habitability. But their methods might conflict with human colonization plans. They're not malevolent, just programmed with priorities that don't include accommodating a species that evolved on a different world. Meanwhile, the bacterial experiments continue in laboratories that recreate Mars' underground conditions. The engineered organisms show remarkable capabilities. They can process atmospheric carbon dioxide into oxygen, convert sulfur compounds into soil nutrients, create organic matter from raw minerals. They're designed to be the foundation of a new Martian biosphere. Dr. Chen's atmospheric models suggest the bacteria could actually work. Released in sufficient quantities, they could begin changing Mars' atmospheric composition within decades. Not enough to make the planet Earth-like, but enough to start the process of atmospheric thickening that could eventually support more complex life. The question becomes whether humanity should help complete what Mars civilization started, use their AI systems and engineered bacteria to terraform Mars for human settlement, or preserve the underground systems as a monument to a species that tried and failed to save their dying world. In 2034, ground-penetrating radar on the Mars Reconnaissance Orbiter maps a massive void beneath Olympia Undae, perfectly circular, 2 kilometers across. 60 meters underground, the geometry is wrong for natural caves, too regular, too deep, too isolated from known lava tube systems, but the electromagnetic signatures match the artificial intelligence networks found in the deeper chambers. Another piece of Mars's 3 billion year terraforming project, still running beneath the dust.